The third limitation for the naive Gauss elimination is about the round-off error. We can use high number of significant figures in the calculation to reduce the error. Besides that, we also can use the pivoting strategy by using the original coefficient instead of the scale coefficient in order to reduce this error. In this example, we will show you how to use the scaling plus the pivoting strategy as well as the new improvement strategy, which is using the original coefficient. Previously, we learned how to standardize the system matrix here by using the scaling. So, based on the maximum element, they divide this 100,000 and then you obtain 1. So, you continue to divide the first equation with this 100,000. You should be able to obtain a scale coefficient like this. So for the second equation, you do not need to perform the scaling because the maximum element is 1. So we just remain it here. Based on this scale coefficient, we know that the largest element must be at the pivot element here. So since the pivot element is very small here, we need to switch it using the partial pivoting. And then after you switch the second row to the first row, we obtain this result. And if you check the pivot element for this new formulation, you found that the pivot element is the largest. Therefore, we can say the partial pivoting is success. In the previous example, we directly continue from this formulation and perform the Gaussian elimination in order to solve the x1 and x2. This is not recommended because when we use the formulation here, which involve the scale coefficient, as you can see, after the scaling, you need high decimal places or significant figure in order to retain the accuracy of the number. If you just let this number to be 0, then you will suffer the round-off error in the formulation. So instead of perform the Gaussian elimination on the scale coefficient, which might suffer the round-off error, we will continue to perform the Gaussian elimination from the original coefficient here. So since you know that your row 2 must be switched with the row 1 due to the partial pivoting, so we just switch the first row here to the second row. And then you obtain this result. Since we are using the original coefficient in the calculation, this can avoid the round-off error in the formulation. Then you can continue for the Gauss elimination method. Firstly, you perform the forward elimination to obtain this result, and then you perform the back substitution to obtain the x2 and x1 solution. To check this solution, you substitute it back to the original equation. If the left hand side is equal or almost equal to the right hand side here, then we can say the solution is accurate.